a great visit so far, and look forward to speaking to you about my work, both in Alaska and in New Zealand. So I actually got two parts to today's talk. I'll bring up the first slide here. So the main idea of today's talk is to kind of give you a tour of two areas that I've been working in. So the New Zealand North Island and the Alaska, Gulf of Alaska off the Copper River. And both of these areas exist on active margins where you have subduction of oceanic plate under continental crust. And that results in a couple of, sort of interesting issues in terms of what we can learn about the history of recent climate changes as well as human impacts on the coastal ocean. And so in this slide, just to kind of give you a sense, and I assume there's a pointer here somewhere, is that right? Does this serve as a lamp or a pointer? That's okay. I'll just stand up here. I got one up in my office. That's all right. I can do without it. So, in the past decade, there's been a lot of interest in active continental margins, and these slides sort of summarize some of those issues. One is you have an extremely high sediment flux into the oceans at active margins because of mountain building and orographic effects. Places like the Indo-Pacific archipelago and the Gulf of Alaska have some of the highest sediment fluxes in the world. When you combine that with the tectonic deformation of the margin, what you often get are subsiding basins which have the potential to contain a very high resolution record of Earth history. And so that's kind of what I'm after in looking at these margins. And of course the input of the sediment to the margin is driven by climate and hydrology and the oceanographic processes which affect the dispersal there. Oh, thanks very much. Sorry. So I'll spend the first half of the talk sort of telling you some of the results from the work that we did off New Zealand as part of the NSF Margins program, and I'll end up showing you some very preliminary results from a study we did just this past year in the Gulf of Alaska. So here's the setup for New Zealand. We're looking right here in the North Island of New Zealand where the Pacific Plate is being subducted under the Australian Plate, and this is the blow-up of the East Cape, and it shows the sediment loads coming in from major rivers. This is the load in metric tons megatons per year. And one of the interesting aspects of this setting is that although the river is a medium-sized river, and the loads may not be impressive, relative to the, say, 200 megatons of the Mississippi, but the sediment yield is very high. In other words, the amount of sediment being eroded from the landscape per unit area is extraordinarily high. So the landscape is being denuded basically as fast as it's building up through uplift. So very high sediment yields. And this is a seismic profile from the margin. I think it sort of summarizes very nicely sort of the potential for a record along these margins. So this is a profile off the margin of northern New Zealand. This is the continental shelf. This is a slope basin. And the scale here is this is a 1 kilometer scale bar. And what you can see is on the shelf is because of deformation, you have rapid subsidence and accumulation of extremely thick quaternary record here. And so again, this confluence of high sediment yield from the margin and tectonic deformation together makes a very nice record. So this is sort of a blow-up of the study area that we were focusing on the east coast of the North Island. It shows Poverty Bay, into which the Waipoa River flows. And you can kind of see this dashed line is the shelf break at about 120 meters. And this is a structural map just showing you a series of anticlines on the outer shelf and synclines on the inner to mid shelf, where you have a fairly thick, as much as 75 to or so meters of Holocene sediments accumulating on the continental shelf. I think it's important to sort of reference for comparison. If you look at the east coast and measure the thickness of the Holocene, it's on the order of a few meters. And so the record there is not going to have the same fidelity as the record here on this active margin. So we had the great fortune to be able to grab the Marion Dufresne, which is a long coring vessel, as it was transiting this area, and collected a series of long piston cores in this area to sort of probe this record. If you haven't seen or been on the Marion Dufresne, it's a huge French vessel. It's actually has a couple of different functions. One is as a supply ship to some of the French Austral Islands. But it deploys this giant piston core. The thing is a monster. It weighs about 10 tons, and they have the record core, I think, that they've collected is something like 60 meters long. So it's a really nice setup to collect long cores and have, to recover great high fidelity records from some of these muddy environments. And so what can we tell from these long core records? What do we get out of them? It turns out that just looking at a simple metric like sediment particle size can tell us a lot about the history of this particular margin. And so this is Poverty Bay, the Waipoa River in here. This is the inner shelf basin in here. And so we're looking at the core just to the north. And this is grain size in phi, so all you need to know is it fines to the right, and this is age down to basically the start of the Holocene. So the cores that we collected, which were up to 23 meters long in this case, penetrated down to the base of the Holocene at 10,000 years. And the grain size shows a pretty interesting pattern. We've got from the base of the core, starting at 10,000, we see a very nice fining trend, which we simply attribute to sea level rise. So the transgression of the shoreline moving landward, the water depths in the basin are getting deeper. You're trapping the coarse sediments landward into Poverty Bay, and so the material that's making it out to this location on the shelf as the water depth increases becomes finer and finer. Makes perfect sense, right? After about 7,000 years, which happens to occur right at the maximum transgression, then the sea level begins to march back out. So this is the shoreline at 7,000 years at maximum flooding. And then with time, this area within Poverty Bay Flats fills in, and more and more coarse material escapes the basin and is able to get out to the shelf. And so the signal starts to become more and more coarse as you move towards the present. So that's just a typical sea level signal, although it's pretty nice to have it recorded in such a nice long record here. What happens after about 3,000 years ago is kind of a different story. So you can see that there's a very abrupt coarsening in this case right at about 3,000 years. And our best guess, and this is based on some work that was published by Gomez and others, as well as our own study, suggests that at that time, which was the time ENSO really turned on, the incidence of cyclonic storms in this area increased, and which resulted in a coarsening of the signature. Now, there's some debate as to how that coarsening manifested in terms, or what caused the coarsening. Gomez suggests that it's actually increased landsliding from intense rainfall that released coarse sediment from the soils. These are volcanic-rich soils in this basin. And so this is kind of a soil signature from massive erosion of the catchment. However, we've more recently begun to question that. We wonder if it might be, another explanation might be that the coarsening results from a more intense oceanographic regime, again related to ENSO and cyclonic storms, where you have a lot more resuspension, and so it's really a winnowing effect. So, just with a simple grain size record, I think one point here is that, we can see a climatic signal within this high fidelity record. The upper change, which happens at the very top of the core, it's not an error. I mean, it's this fining that happens. So the fining that happens over the last few hundred years equals everything that we've seen over the entire Holocene, and that's undoubtedly a human signature. So along this particular margin, we're seeing the influence of human deforestation, which increases the fine sediment load of the rivers way out on the continental shelf. And so, our changing land use practices are now part of the geologic record in the Anthropocene. So just a little more data, a few more data slides just to underscore that. So these are the profiles so this is 3007. This is the one I just showed you, the grain size here, coarsening and then fining again. And but I also show here the delc-13, which gives us an indication of marine versus terrestrial signatures within the sediment. And the one thing that is, so like the grain size metric, it also, for the most part, makes sense. So if you take, for example, this one, 3004, this middle panel, you can see these open triangles are the delc-13. You see a fairly marine signature at first, then it becomes more terrestrial after the maximum transgression. But then you get this blip back to marine, and then another blip back to terrestrial. And it's quite a large excursion, and we don't have a good density of data, but we're wondering if one of the ideas is that we might be seeing sort of an example of human fertilization of the coastal ocean, either in a combination of probably Polynesian slash and burn, and then wholesale deforestation by Europeans. One idea is that you're releasing a ton of nitrogen out into the ocean, and it's creating this marine carbon signature, and then the return back to a terrestrial signature is a result of later land use practices, which correspond with the increase in fine sediment discharge. So just at this point, it's a hypothesis, I guess. So we looked at this a little more closely from the perspective of sediment budgeting, and the way that we did that was, this is from a paper by Tommy Gerber and others, which shows a couple of transects across the shelf off of the Waipoua River. And one of the things you can make out here is, first of all, you can see the basins. This is the southern basin and the northern basin. But within each of these profiles, you can see really nice layers which stand out, these reflectors here. And we were fortunate in this area in that we can correlate these reflectors to tephras. New Zealand contains, the North Island contains one of the most active volcanic centers on Earth, the Taupo Volcanic Center. And so the record of volcanic eruptions which spread out over the shelf are pretty well documented. Their geochemistry is known and they've been well dated. And with our long piston cores from the Marion to Frayne, we can clearly see this is an ash fallout tephra in the right-hand photograph of that section of the core. It shows up in the core log in both the magnetic susceptibility as well as the gamma log. And in terms of depth, it corresponds very nicely to these reflectors. So we've got this basin, which has a very high rate of sediment input, and then we have these lines through the basin. We know the exact ages for. And so from that, what we can do is actually budget age by age period based on the ages of these tephras and the volumes calculated from the seismic data. So based on that, we looked at 3 different time slices. So those were the tephras that were available to us. So this is in calendar years before present, 3410 to 5530, 1718 to 3810, and the present to 1718. And so the sediment volumes that we calculated based on the seismic is in these light squares. And the estimated paleo discharge of the river supplying sediment to this area is in the dark squares. And based on that comparison of what's been captured in the basin to what we think the river's been discharging, looks like that there's a balance within error of sediment input from the river and capture in the basins. So over long time scales, the balance of sediment input to sequestering on this particular margin pretty much balance out. Becomes a little more interesting when you look at the changes that's happened because of land use practices and increased sediment loading to the rivers. So what we wanted to do was, those longer term averages were just that. They were bulk averages over those millennial timescales. To look at the human impact, you have to really look at the past 100 years. Human deforestation in the Waipoa catchment, or I should say European deforestation, was really late 1800s, like 1880 to 1920. And so the effect of that massive deforestation has only been around for 100 years or so. So we needed to look at a different way to estimate the sediment volumes being captured on the shelf at the present time. And the way we do that is, as Jen mentioned, I do a lot of work in radioisotope geochronology, and one of our standard stock trade tools is lead-210 geochronology. So through the margins program, we collected a gazillion cores and ran a gazillion lead-210 profiles. And so without getting into the details, you look at activity of lead-210 versus depth. It's got a 22.3-year half-life. And so you can estimate the sedimentation rate based on the slope of the profile. And from that, because we had such high data density, we could actually develop a sediment budget on a 100-year time scale for this shelf. We also verified this. This is I should put in a plug for plutonium since Jen mentioned this. We use bomb fallout isotopes like cesium-137 because we know the history of their input. There's a maximum input in about 1963, right ahead of the Test Ban Treaty. Unfortunately, in the southern hemisphere, cesium fallout wasn't so high. It's about a factor of 4 to 6 less than it is in the northern hemisphere. So the signal wasn't very good. So we started to think about other bomb tracers, and one is plutonium, 239, 240. It's been around for a while. The difference nowadays is that you can measure very small quantities of it based on ICP-MS. And so we can measure minute, atom quantities of this stuff and come up with beautiful cesium profiles which help to verify our lead-210 accumulation rates. So one of my students, former students, Annie Miller, for her master's thesis, generated this map. And this just shows the distribution of accumulation rates based on this dense lead-210 data set. And she created a sediment budget from this. So and if you do the math, it looks like we can account for about 3.6 times 10 to the 6 tons per year. Remember that the discharge from this particular river, the Waipoa, is 15 times 10 to the 6 tons per year. So it looks like at the present time, we've only got about 18 or 30% of the discharge, and it's fairly well gauged. The river is fairly well gauged, so we know what it is. But there's only a small amount of it accumulating on the shelf. So putting that into perspective with our longer-term view, so this is both the long-term and the short-term data sets together. So remember, over millennial timescales, the input and the sequestration on the shelf are in balance. If you look at the last 100 years, this is the input. This is the input here, this tall bar. So that's the present load of the Waipoa, which is hugely much more than what it was in the past because of land use change practices. And here's the sequestration. So where's all this stuff going? We don't, probably some of it's going right off the shelf. Some of it may be carried with coastal currents on up the coast. But I think it's rather phenomenal that not only do we see this huge human signal in terms of texture and the organic geochemistry of the surface sediments of the continental shelf, but we've also shifted the mass flux of this major input so that instead of a shelf which is retaining most of the material flux from the river, it's actually exporting it to the deep sea. And that may have something to do with, you're changing from a relatively coarse to a relatively fine sediment, so it's going to change the dispersal patterns. But in any case, we're having a major effect in the coastal ocean in this particular example, and you can see that human signature prominently in the sediment record and in the sediment budget.
So how do you know the historic input or the prehistoric?
That's a little more difficult to get to, so that's a great question. We don't have river aging estimates, back that far, obviously. And so a lot of these were estimates based on the Ketterer model. One of the things they looked at is lake records. So they looked at varving in some of the lakes in nearby catchments and looked at the shift in terms of the thickness of some of the banding to figure out what the paleo discharge was relative to the modern discharge. So I guess the answer is it's scaled to the lake records. That's probably our biggest, but you're right on point with the question because that's one of the bigger uncertainties. So I guess to recap the New Zealand results before I transition into Alaska, we've got this wonderful signature in the textual record of transgression, regression. We see ENSO, increased storminess probably, and this humongous signature of fine sediment from humans. Maybe a human fertilization event and a sense that we may be changing the mass fluxes in the shelf from capture to bypassing.
Hey guys,
yeah, sure.
Before you go to Alaska.
Yep.
You should be going to Alaska.
Yes, I'm going to Alaska.
What about the coastal system? Did the coastal system change significantly? The coastal morphology, the progradation of the spits? How about the rivers? Did it change from a braided to a meandering or vice versa?
Well, the rivers in they have levee guides now in the lower Waipoa River. You can see one of the things that you see actually. The river's been it hasn't been paved over like the Mississippi. They do have some river guides. One of the big changes that you see in the catchment because of the increased sediment loading is huge rates of aggradation in the floodplain. It just, starting about 100 years ago, I mean, the floodplain is just zooming up. And so, you see it I mean, that's one of the big signatures that you see.
Is that part of the missing 70%, or?
No, I don't think so. But that hits on another sore. It's always a sore subject in terms of, what is missing between the river gauging station and the mouth, and so, I haven't done that calculation, but my guess is that may account for a small fraction, but probably not the six-fold increase that we're seeing. Okay, so going to shift gears now and take you, and this is kind of more of a more tourish rather than science-ish, but and this is some work that we've been doing recently, funded by NSF, a RAPID program. If you look at the sediment yields from North America, and you see a couple of big arrows, and one is, of course, the Mississippi River and the Gulf of Mexico. And the other one is up here in Alaska. And again, this is an active margin where high rainfall, high uplift, erodible rocks lead to very high sediment yields. And so we had an opportunity to, which I'll describe in a moment, to look at the Copper River this past summer. So this is just to give you a little background on the copper. So this is Alaska, Gulf of Alaska. This is our study area. And then this is a blow-up showing the drainage basin for the Copper River. So Copper River is the major sediment supplier to the Gulf of Alaska, there are two mountain ranges, which I'll come back later. I'll mention them again. I just lost my pointer. That's okay. So the Wrangell Mountains to the north and the Chugach Mountains to the south. And then just Prince William Sound is over to the west. So just to kind of, I'll come back to these, but the main point I want to make now is that these mountain ranges are part of accretionary terrains in this collision margin. They have very different rock compositions and different chemical different elemental compositions. So where does the copper sit in terms of sort of its size and discharge relative to some common comparisons? Okay, so the Mississippi is obviously one of the big references for us. I mean, it's got a fairly big drainage basin. The elevations range up pretty high in the Rockies. And the overall sediment discharge in megatons per year is fairly high, but the yield is not so high relative to the copper. So the Copper River, which has a much smaller drainage basin, higher elevations, moderate discharge, high runoff, and high yield. So if you look at the sediment yield, again, sort of a measure of how much sediment is coming off per unit area per time in these mountainous collision margins, it's phenomenal. Okay, so how did I get to go to Alaska? This is what brought us there. It was literally this amazing event back in January, in the week of January 18th of 2012. They had 6.1 meters of snowfall reported in Cordova. you know, we just heard about this recent little flurry that they had up north, you know, which was about 3 feet. People were kind of excited about it. Well, it's 6.1 meters in this area, and this is a place that's used to a lot of snowfall. So we felt that that was, oh, and here's sort of, if you go back to you can go back to 1950 and look at the integrated snowfall from December to February, and what happened in 2012 is like nothing we'd ever seen before. So we used this as an in to ask for a little bit of money from NSF, just because we felt like with such a high snowfall event during the winter, we had the opportunity to monitor a potentially historic spring melt of the Copper River. And so they bid, and they threw us a couple of dollars, and we were able to get up there to look at this. And I just want to tell you a little bit about what we found. So here again is the snowpack this is from April, way above normal. And one of the things, in addition to wanting to look at the outflow of the copper and the sediment dispersal from the copper into the Gulf of Alaska during the spring melt, we are also kind of interested in tracing where this material is ending up. So this is the mouth of the Copper River. This is actually from 2011, but what it shows is the typical situation where the currents in the Gulf of Alaska sweep the sediment plume towards the west, and this plume actually enters, and you can kind of see it here. It's a bit faint. It actually enters into Prince William Sound. And we have pretty good evidence that Prince William Sound, which was a deeply scoured fjord after the last glaciation, contains a pretty thick Holocene sequence. So remember on the Waiapoas shelf, we were looking at something like a 75 meter or so thick at maximum. Here in Prince William Sound, you've got something like 150 meters of Holocene, and it's just horizontally bedded. I mean, so in terms of looking for a place where we might extract a record of past climate, we felt like this was a good place to look, so we were poking around up there. So just a couple of things that we were able to do during our trip up there. This is the road out from Cordova towards the Copper River. We still had a bit of snow on the ground, but you can see. I mean, this river is pretty turbid, and I just want to give you a sense of what it felt like. We came out to the bridge on the way to we tried to get up to the gauging station, which is where the $1 Million Bridge, which was pretty far up the basin. And we came to this particular bridge before that, and it was washed out. The river had scoured through the far end, and so we couldn't take the car across. But we wanted to get some suspended sediment samples, and it's hard to see in the picture, but I think that just to kind of give you a sense of what this river is like in its full fury during the spring melt. I mean, it was ripping. We're out on this bridge.
Oh man, I can feel the bridge moving
And
here.
you can literally, the bridge is kind of going back and forth. And here's my colleague and former student, Tim Dell, kind of trying to get a water sample off the bridge. You can see out here the sample bottle is just speeding away.
I think it's going.
So, needless to say, we survived the experience, but it was pretty awesome to see the full fury of the Copper River. So we actually had a very successful sampling trip using local vessels. I mean, we had a small sort of converted trawler that we used to collect a series of gravity cores in Prince William Sound, and then along with the Prince William Sound Science Center, had about 17-meter, I think it's, it might be, no, it's 17-meter aluminum research vessel that we were able to get out, and we were doing some water column work as well as seabed sampling off of the Copper River, right off the mouth. So, when we planned this short trip, because we didn't have a lot of money, we just had to sort of guess as to, when is the flood going to come? When's the spring melt going to happen? And you never know. The hydrograph for the copper varies from year to year depending on the climatic conditions and how much snowfall there's been and how fast summer cranks up. But we guessed late June. These red bars are actually when we were out sampling, and the overall line is the hydrograph. So this is the spring melt peak, and we hit it pretty close. So we were out in Prince William Sound at this point, and then just after the peak, we were out off the Copper River. There's another later peak, and then actually this past year there was one in October. I'm not really sure yet what caused that. It could have been a eucalyptus, which is an outburst event in the Copper River Basin, or maybe another odd sort of warm period, which caused that peak. But in any case, we hit the spring peak. This MODIS image actually was collected from when we were out there, so you can see the river. So we had good luck in timing. We also had good luck in weather, because going out in the Gulf of Alaska in a small aluminum boat is a dicey proposition. And so you can see the conditions that we were out were pretty favorable. And we certainly saw the plume coming out of the river. This is from 10 or so kilometers offshore, looking towards the Copper River Basin. And you can see you can put your finger on the front here from the river coming out. So just a couple of words about one of the things we were trying to accomplish at the mouth of the Copper. We attempted to use another tracer, cosmogenic beryllium-7, which has a very short half-life. It's formed in the atmosphere, comes out in wet and dry precipitation, it's particle reactive. And in the last 10 years or so, it's been used as a tracer of river input. A lot of it is locked in the catchment. Studies off the Eel River in California, the New Zealand rivers that I talked about earlier, and the Po River have all shown this great relationship between river input having a nice high beryllium signature. So you can look at and trace this water coming out. But the idea was we'd be able to trace the Copper River suspended sediment plume over into Prince William Sound using this beryllium-7 tracer and get some idea how fast it was moving around. Well, sometimes in science you don't get exactly what you expect. And so when we measured beryllium off the mouth of the Copper, there was nothing there during this major flooding event. And so we learned something new, which is that the paradigm of beryllium-7 being a tracer of river input is not always true. And in this case, we think it relates to the fact that most of the water coming out in this first pulse from the spring melt was from snowpack that had been sitting around since January. And so most of the beryllium-7 with its very short half-life had decayed to nothing. And so the rivers coming out were depauperate beryllium. So that was kind of a wash. The coring that we did in Prince William Sound was a little more productive. And I want to talk about, I'll show you some data from two core sites that we've looked at. One is right at the mouth of Hinchinbrook entrance here, P7, where the plume of the Copper River enters into Prince William Sound, and the other one in the north part of Prince William Sound, near to the Columbia Glacier. I do have to digress, and this is kind of just tell you that this, we were sampling from this converted trawler, and this is really old school stuff. We had a bucket of line, so about 1,600. The water depths that were gravity coring in Prince William Sound are approaching 500 meters. So this is not shallow water shelf sampling. We had a crab pot winch, and so the tension on the line is all being applied by two plates, which are squeezed together So the friction is holding the line in. And the surprised look on my graduate student's face is had been just after the rope came off that crab pot winch and the core free fell 500 meters to the bottom. We got a perfect core. But you should have seen the people running away from that bucket of rope. Okay, so the cores actually had some very nice records. We looked at the two cores, the one at the mouth of Hinchinbrook and the one up towards the north of the Columbia Glacier, and we did our normal geochronology dance. We measured the lead-210 activity, and this is almost 150 centimeter core. You've got excess lead-210 down at the base. You can get, if you draw a regression line through that, you get accumulation rates of about 6 centimeters per year. So that stuff is just piling up at the mouth of Hinchinbrook entrance. This is the cesium-137 profile. You can see we see cesium-137 throughout. So all that stuff had been deposited after 1950. If you look at the core X-radiograph itself, it looks varved. It's just layer by layer by layer. And so there's no bioturbation or disturbance of the signal within this core. Up to the north, near Columbia Glacier, you can see what we think is a turbidite layer in the X-ray radiograph. So that light layer is a sand layer. It's hard to see it here, but it's scoured at the base. Turns out that if you look at the cesium profile, the peak in the cesium profile is right here. The turbidite is right there. Now the turbidite, the activity in the turbidite is low because it's sand, and so there's not much radioactivity associated with the sand because it's got a low surface area. But the fact that those peaks are so close suggests to us that turbidite may have resulted from the Great Alaskan Earthquake in 1964, because that's the peak of the cesium. And for those of you who don't know, the Great Alaskan Earthquake, magnitude 9.2 in the moment scale, was the second greatest earthquake recorded in history. I mean, it just rocked the place. And this is actually a picture of Anchorage, I think, which was way away from the epicenter, which was in the north part of Prince William Sound. So here's the epicenter, right over top of Prince William Sound. So, again, one of the main thing that we were trying to figure out here is if, do we have the opportunity to kind of develop a high-resolution climate record based on what's happening in this particular, it's kind of a unique environment. I mean, you've got the Copper River, there are different discharging from different catchments in terms of the mineralogy, and so we thought we just take a look at the elemental composition, downcore elemental composition, and they've got this great gizmo up at the IODP facility in College Station. You can zap your core through it and look at elements from silicon up to uranium at pretty high resolution. So we scanned a couple of these cores at about half centimeter resolution just to kind of see what we could pull out. And this shows silicon aluminum ratios. And you can see there's a pretty nice, and this is depth in the core in millimeters, you can see a pretty nice periodicity. A couple of big spikes here. We think that the large spikes are because of silicon-rich tephras, which are deposited from a few historic eruptions to the north. And we also looked at this, we kind of looked at the signal. This is actually a different ratio. We looked at zinc to sulfur, which showed a really nice periodicity. And because we had the lead-210 accumulation rates, we know the timing, and we just ran a simple fast Fourier transform to look at the look at the dominant frequencies within these and so what we ended up with is a really nice annual signal. And so we're thinking at this point that the Copper River annual discharge hydrograph is recorded within Prince William Sound, and that the zinc sulfur, in this case, the high zinc is recording inputs from the northern Prince William Sound area where there's a series of sulfide deposits, and the valleys or the low points are the Copper River signature. So the variation between Copper River and local inputs is creating this periodicity. So we're pretty excited by this. The other thing that we looked at, the more we look at this, the more that it appears that we've really kind of got we've hit a gold mine in a sense. So we looked at strontium and manganese, and this is from the Hinchinbrook core at the mouth where the Copper River plume enters, and this is roughly a 23-year record. We know that from the lead 210 dating, and you can pretty much eyeball the fact that you've got a strong annual signal, and if you look at one of these annual peaks, many of them seem to be, you can deconvolve them into a low peak and a high peak as you move forward in time. And we're actually starting to, and in addition to that, you're seeing this is just a third order polynomial fit, and you can kind of see some decadal frequency. We can't pull that out with a fast Fourier transform because we don't have a long enough data set, so it's kind of subjective at this point. But certainly the annual frequencies and subannual frequencies that we're able to pull out, I think, are really intriguing. In terms of these subannual frequencies, our working hypothesis at this point is that during the spring melt, most of the water and sediment is coming from the Chugach range, which has a lower strontium concentration relative to the Wrangell Mountains, which mostly are supplying water in the late summer when the high mountain glaciers melt. And so, it looks like we're really starting to hit on the potential for getting at the kind of details of the hydrology of this basin and how that might vary over subannual, annual, and decadal frequencies. So we're kind of excited about it. We're thinking forward into maybe trying to get some longer cores from this area, maybe tied in with climatic variations that we know affect snowfall and summer temperatures in the Copper River Basin, things like the Pacific Decadal Oscillation and the Arctic Oscillation, which in some cases you can tie to. This is a local discharge record. This is just sort of a teaser. So, for the Alaska, to recap the Alaska results, we're just starting to scratch the surface. Some of the XRF data we've just looked at in the last few weeks. But I think we've got, really, really great potential for kind of looking at climate, the history of climate in an area that, certainly in the future is going to experience much more rapid change. And so understanding kind of the backdrop and what's happened naturally over the Holocene, I think will ultimately be important to us. And that's my talk.